This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Good afternoon, everyone. This is working good. So as you know, next week is the teaching break. So no lectures, no workshops, no consultation hour. And the week after we continue, and the workshop, machine learning workshop, continues the week after the teaching break, because many groups told me they haven't finished it yet, so that gives you one more week. And I will also cover during that time the supervised learning, so hopefully we'll finish the unsupervised today and then go to supervised learning. Yep. I also remembered what I was going to say as the second point about probability. I'll tell it when I cover the other the Gaussian mixtures. So first, the principal component analysis. That's the very classical tool for dimension reduction, and we discussed why it's a good idea, making the problem simpler and computationally more feasible. And there are, of course, other ways of doing this. There are a lot of variants. Also, autoencoders are popular methods, but PCA is a classic, and it's, I think, worth mentioning and going over. So the idea is we map the data set with having dimensionality d. So each vector of the data is d dimensions, and we map it to a lower dimensional space. This is a pictorial representation from 3 to 2. Three-dimensional red dots are mapped to the black dots on the plane, two-dimensional plane. Right? So how do we do this? I made a small correction here. I'll post it, the updated version. The idea of the PCA is so, and I mentioned there are maybe many ways of mapping these things, right? So what criterion are we going to use? PCA uses the criterion of maximizing the variance of the projected data. So kind of the underlying intuition is retaining the diversity of the data. You know, if you map everything to a single point, yes, it reduces the dimension and everything, but that single point won't tell you much, right? So it is possible to reduce everything to a single point, I mean, or by taking the mean, right? You can take the mean, and then you have a single vector, just like k-means clustering, single cluster, single prototype. But just giving that single prototype doesn't tell you much about the underlying data that created that prototype. So obviously, we want to retain the richness of the data, and then maximizing the variance of the projected data is kind of a nice way of retaining that richness. So I will do the derivation on the one-dimensional space, because this is a really nicely instructional and a first step towards doing m greater than 1 dimension. So what we have here is x. Each x is a d-dimensional vector, right? Xn is a d-dimensional vector, and then we map everything each x to a single-dimensional space, so they become single points on a line, and that is y. So each x becomes y, and the mapping is this u, which is here shown as a dot product. So x is also a vector, u is a vector, and then the dot product will give you a scalar, right? And dot product here is the transpose times x. So if we look at the mean of the data, that's the mean of the data, and then we said we want to maximize the variance of the projected data. That was this typo here. So the variance of the projected data will be done by definition this, right? So this is the y n and minus yn bar, because this is the yn bar will be then u transpose u1 transpose x bar. So subtract the mean, take the square, sum over the data points, take the the 1 over n, so you get the variance. And if you define S like this, so after a little bit of playing with the vectors and matrices, you can write it in a nice quadratic form like this, U transpose SU, where S is defined as the covariance matrix, right? S is then, because it's a covariance matrix, it's positive, definite, semi-definite, and symmetric. So that helps with the taking the derivatives, makes it easier. So So yeah, that's the quantity we want to maximize. So if you want to maximize this with respect to u1, and this is quadratic, well, the issue is you can maximize it by making u as large as possible, right? So you make u large, then this will be large. Then what's the point? So we should put some additional constraint to this, and that would be the constraint of, let's say we put a normalization constraint. We ensure that our mapping has some type of a norm equals to the 1. So that would be then u transpose u equals to the 1, right? So this is then we are looking for a normalized mapping that maximizes the variance. We don't want to map x's to very large y values. So we want to keep the y values reasonably large, but also we still want to maximize the variance. So then the maximum variance projection problem is maximized u1, and then this term objective such that the normalization constraint, right? It's a basic constraint optimization problem, right, as we have discussed before. So what we do is we write the Lagrangian of this linearly constrained quadratic problem, and once we, that would be an equality constraint. Notice that there is only one constraint here. So because we have only one constraint, there is only one Lagrange multiplier in this case. And if we write the KKT conditions, we end up with this equation. So we have SU1 star and lambda U1 star. So if you multiply from the left-hand side, because U1 star transpose times U1 star is normalized to 1. So the right-hand side, you only have the scalar, and left-hand side, we have this scalar as well. So maximizing this is equivalent to finding the largest eigenvalue. So then U1 star, here this is the definition of eigenvector associated with S, covariance matrix. So because it is a eigenvector, that is the eigenvector corresponding to the largest eigenvalue, right? Therefore, this eigenvalue is called the first principal component. This is the largest eigenvalue of the covariance matrix. And if we want to project to 2 dimensions, m equals 2, we can repeat this process. It turns out with the, and we will see soon, you can repeat the process with the second largest eigenvalue, third largest eigenvalue, and you take the corresponding principal components, and all these dot products, give you the combined mapping will give you the y that we are looking for. There should be there should be a transpose here. I think I need to correct this, because then each of the dot product will give one dimension of the vector y vector. It should be U1 transpose, U2 transpose, UM transpose. So I should put a transpose to this matrix. So I will do that as a correction. All right, so that's the idea. So maximizing the variance is equivalent to choosing the largest eigenvalue and corresponding eigenvector. And then for one dimension and more dimensions, you choose the largest eigenvalue. So that's a maximum variance formulation of principal component analysis. So we want to retain the richness of the data when we map it to the lower dimensional space. As I said, intuitively, think otherwise. You could have mapped the whole data to a single point. That would be the minimum variance counterpart of it. So, of course, retaining largest variance is a good idea. Other interpretations, you can also, because PCA is something very fundamental, you can interpret it in multiple ways. Actually, you can start with a equivalent formulation by starting with this cost function, mean error of the approximated xn, the mapped one minus the original one squared, distance. And if you minimize this cost, you end up with the same thing. But this cost, it's also shown that this cost is equivalent to the remaining sum of remaining eigenvalues. So minimizing this cost means choosing smallest, make sure that the smallest eigenvalues are left m plus 1 to d. So that's again equivalent to choosing the largest m eigenvalues for the mapping. Or there's yet another interpretation, singular value decomposition. So you can write the whole data set, d n points and d dimensions. So each row will be a data vector. You can write it as a principal, singular value decomposition, U as V transpose, and S will contain the eigenvalues and 0. And then if you choose, again, the top eigenvalues, you get an approximation out of this whole thing that is roughly equal, retains roughly the main idea of the X. So that's another way of thinking about it. All right, so I haven't gone too much into detail. I just mentioned these, that they exist. You can go read the whole story. Nice lot of matrix algebra, linear algebra here, especially for this case. All right, so this question allows us to go through this little bit and proof by induction to show that the linear projection onto an m-dimensional subspace that maximizes the variance of the projected data is defined by the m eigenvectors of the data covariance matrix corresponding to the m largest value. So we have shown it for m equals 1. Suppose this result holds for any general m, then if we show it that it holds still for m plus 1, given that it holds for m, that's the proof by induction, right? Because it holds for 1, it holds for any m plus 1. That means I start with 1, 2, 3, 4, 5, until infinity it holds, right? So that's the proof by induction. And I just figured I can switch this easier. Let's see, we can do this pretty quickly together. I'm sure you can do it yourself too. We have music too, you see, like it's a nice, we have music, we have nice things. So then what do we have? We have, we assumed that we have u1 to um already there. Oh, okay. Why is it not showing? Just a second, sorry about that. I guess I need to end this slideshow. Didn't work. Easy switching didn't work. So we have u1 to um, and corresponding to the m largest eigenvalues, right? And then we are looking for um plus 1. We need to choose a um plus 1, and then needs to be orthogonal to the other ones. And how do I impose that? I just make sure that the dot product between ui and um plus 1 is 0 for I equals 1 to m. So I need to impose this orthogonality constraint. And another constraint I need to impose is this normalization, um plus 1 transpose. Again, that's the same as dot product as well. So that should be 1, right? So that's the other constraint that I'm imposing. Maybe delete this to not confuse. And then I just write the Lagrangian under these constraints, maximize, find the um plus 1 such that um plus 1 transpose S um plus 1 is maximized subject to these constraints, constraint 1 and 2. That would be 1, that would be 2. All right. Then what do? We write the Lagrange multiplier, and then Lagrangian will be then um plus 1 transpose S um plus 1 plus lambda, the m plus 1 first lambda, 1 minus, these are all equality constraints, 1 transpose um plus 1, plus all of the orthogonality constraints. I need to impose them, plus I will have I equals 1 to m, let's say eta I, these will be the Lagrange multipliers, then um plus 1 transpose ui, right? So if I take the derivative of the Lagrangian with respect to um plus 1, S is symmetric, So if I take del L del um plus 1 equate to 0, I'll end up with 2s um plus 1. In this case, this would work because s is symmetric, minus, again, we have against a square here, so we have got 2 lambda m plus 1 um plus 1, and then plus eta I ui, because these will be I equals 1 to m. So if I multiply this now from left-hand side by, that's not clear, so this is 0, so this is, let me write it this way, 0 equals. So if I left multiply by um plus 1 transpose, then I get 0 equals then two, what do I get? Um plus 1 transpose s plus 1 minus 2, then lambda m plus 1, um plus 1 transpose um plus 1, that's 1 because of normality, plus all of these actually are orthogonal, so these get 0, therefore this is 0, so we get 2's cancel out, and I get multiplying it, let me see, if I can put it here, so I get s um plus 1 equals lambda m plus 1. If I let me see um plus 1 transpose here as well, right? So we have the same situation as before. Maximizing the variance is maximizing the max this is equal to max lambda m plus 1. So we need to choose the next largest eigenvalue as we were discussing. Therefore, the result holds, and induction argument holds. So if m is the correct one, then m plus 1 is also the correct one, and the lambda m plus 1, the next largest eigenvector, is used for the m plus first dimension, and then that concludes the argument for inductive step. So, and you can go until of course m is less than d, less than equal to d. If it's equal to d, then it's an identity mapping. There's nothing that you're projecting. Okay, so that's kind of goes beyond the first step, gives you the kind of the picture regarding the, and then I have a lengthy solution with a lot of words that you can also read about. I'll post it as soon as I can. So let me see. What else were we saying? That's actually it for PCA. I kind of keep it short. It's a fundamental machine learning method, but that's not the actually most popular or best method that's being used. It's a very fundamental method. It's of course used, but that's not the fanciest method to use, I should say. Maybe it's the classical method to use for dimension reduction. There are many other dimension reduction techniques that work different ways. I'm not going too much into detail on those, and if necessary, maybe let me see, I'm still preparing the slides on the neural networks. Maybe I'll put some slides on autoencoders which do a similar function but with a nonlinear mapping. In the case of autoencoders, you're also mapping things to a lower dimensional space. All right, any questions? If not, let's come to the probabilistic approach to to estimating the distributions. So Gaussian mixtures and expectation maximization, they are two different things, but you can use Gaussian mixtures to represent a distribution, and then use expectation maximization to find the right coefficients of the Gaussian mixtures. So the idea is this. So we can use a sufficient number of Gaussian distributions with appropriate means and covariances. They may differ. Each of them may have different mean and covariance. And then coefficients in the linear combination. We can approximate almost any continuous density to some arbitrary accuracy. So we are creating the px is the distribution of my data, right? And then I'm doing a linear combination. This is a linear model, linear in the distributions. And in this case, the S distribution, I use normal distribution of x with some, each component will have some mean and variance, right? These are multivariate. And then mixing coefficients, probabilities are these pi k's, so I'm kind of mixing them with certain weights, and then this weighted sum will be the p of x representation of p of x, right? This visualization is nice. So you can take one Gaussian, another Gaussian, another Gaussian, you add them up, multiply with the pi's, so you get this nice red distribution, right? Imagine you are given some red distribution. You can approximate it with 3, 4, 5 Gaussians together. It's a bit like what we did with regression. We were using some basis functions to sum up to approximate a function. Now we are adding up these Gaussians as basis functions, and then with some weighting, I add them up to get any distribution. So this is a nice two-dimensional version. So I add 3 different Gaussians, different variances, different shapes. Variance matrix gives the shape. Means are different. They are located differently on the two-dimensional plane. So you end up with this, and it looks like this, right? So this is a very complicated looking distribution, but it's in reality nothing but 3 Gaussians added up appropriately. All right? So this shows the power of probabilistic models, right? You are given a data set, you can actually do this probability distribution. So which brings me back to the point I was making yesterday, and the second point that I forgot to make. So I was saying the probability theory is very, very useful. It's our kind of go-to tool when we want to handle uncertainty and we want to figure out things. But I said I have 2 reservations regarding that. One was just seeing the data as a distribution like this. The data may have a lot of behind-the-scene process, physical processes generating it. Reducing it to a distribution like this is a bit too much reductionism, right? It's still useful. And the second thing I forgot to say was, you will never ever know the underlying distribution, true distribution, unless unless in an academic setting, unless you are generating your data set yourself from a distribution, right, in an IID process. How are you going to check whether your approximation is close enough or not to the data? There is no way of knowing it. There is a true distribution that will always remain unknown. So that's also the second reservation from the probabilistic model. So the mathematical object and the reality will always have a certain gap. So therefore, it is good to have a mental tool and a method, but one should know the limits of even the most powerful methods. So that's the downside. So another way of writing it is this way. So this is actually more general than the mixture of Gaussians. Actually, you can use mixture of anything you like. Because P of x, as we know, we can write it as P of k, that's the kth model, and then P of x given k would be the conditional distribution of the kth basis function, right? And then in this case, then for the previous case becomes a special case of this, where pi k is the pk, and this Gaussian is the px given k, right? So that's the kth model, and the probability of the kth model, and then all of them summed up, k of them summed up, it gives you an approximation to the px. And px is the probability distribution of your data set. Of course, there's also the important question here is, actually, you don't have to make an IID assumption here. The px could be a joint probability distribution, right? So You don't have to make an IID assumption, just the underlying distribution is Px. All right, so then the issue is, how am I going to find these pi's and then the individual means and variance matrices and vectors of the Gaussian distributions, normal distributions, right? So that's where expectation maximization comes into the picture. So before going there, though, like, let's look at one definition that will be, because we are using Px given k. As you can suspect, Bayesian theorem will kick in at some point. It's actually appropriate to write Pk given x, and then we define this as gamma kx. So this can be written as the joint probability of xk divided by Px, basic probability, and the joint can be written as this way. And the bottom line is we can write also Px as any sum with L, PL, PXL, right? So this is this mixture, and then the top one is the kth one, pi k, and then if we choose this to be Gaussian, then it's the normal like this. So these are the posterior probabilities. These are known also as responsibilities. So that's just the name for this ratio, the responsibilities. This gamma is the responsibility, and this will pop up pretty soon. For the entire given data, right? Now actually I'm making an IID assumption here, because if I write the log of the likelihood function for the entire data, ln of Px given all this stuff, right? So now my theta, remember this is the log maximum likelihood we have been doing, it's the same story. So in this case the theta is these three vectors, right? And two vectors and one multiple vectors and then the multiple matrices, and then the pi vector, Px given theta, and then I maximize that, and then under the IID assumption, it's a product rule, and then if I take the log, it becomes the sum over the data points, right? Now I am making an IID for sure, and then this is over the sum over the data points, 1 to n, then the log, if you write it down for the and then for the Px given individual ones, then the pi k is here, and then this is the mixture, right, of the mixture that we have defined here, right? So pk and this, or in the previous page. So once we write it there as a conditional, so this is conditioned on the parameters of individual components of Gaussians that we are adding up. So this is the mixture model, and then log likelihood of that mixture model, x given this. So we are doing a maximum likelihood estimation of the parameters. All right, so yeah, here I mentioned, yeah, the data is IID, therefore the product becomes sum under the logarithm. So that's kind of wasn't obvious when you write it down. It becomes a bit more obvious. Here's the story. Now, how do I find this? How do I find this? How do I solve this maximization problem? So I have the objective function, now log likelihood function. I'm doing maximum likelihood, so I need to maximize over theta. In this case, the pi and mu and sigma. And then I want to maximize this. It's a bit of a complicated maximization problem, and there is a step-by-step solution, like we were doing in k-means, very much like what we do in k-means. We initialize the values of all the components. We again choose the k, predetermine the capital K, how many components, Gaussian components we want to have. And then we do in the expectation stage, we evaluate the responsibilities based on the current parameters, find the gamma, and then in the maximization stage, given the gammas, we find the new mu's, sigmas for each k, and the pi k as a ratio, and then this ratio is simply sum of the responsibilities divided by n. So that gives the mixture probabilities. So that's actually an implementation of expectation maximization. And just like in k-means, it's a two-step process. Each step you do something, and then you use the E's result in M. Then you go to the next iteration. The new values you use to find the next gamma, next step gamma, and then next step gamma is to find the parameters, essentially the thetas, the parameters of the model for the next step, and you iterate. So here's the summary, and then the summary and the question, which I turned into a question. So we want to maximize this, and one can show that maximizing this means using these maximizing this involves finding these, essentially the equations that are here. And I'm gonna, let me see how much time I have. So I have a little bit of time, but I guess I'll go over it a bit quickly, like how many slides do we have? So we have still some things to cover. So I think I'll give you the results, and then we will discuss it over the solution. So once you write the formula, and then let me write it down. This is too much. So let me write it a bit down, and then I'll give you this anyway. So here's the question. Yeah. I think I need to write down the basic idea here. So we want to take the derivative of the objective, essentially. We want to take the del ln del with respect to mu k. If I take the derivative of sum, which is ln px given theta, right? And theta are the parameters. That would be the same as this sum ln. So that would be n, and then there's a k sum pi k, and the Gaussian distribution of xk given mu k sigma k, and that's what this is I put it here for the convenience, right? So close the parenthesis. So if I take the derivative of this, the derivative of logarithm del mu k ln f of mu k would be then f prime of mu k divided by f of mu k, right? So the inside of the log will be, first you take the top part's derivative and then divide by the itself. So once you do that, and then equate it to the 0, so we have got 0, we take the derivative, so we need to write it down inside the logarithm as it is, as we discussed. So the outer sum remains, so we have the outer sum of n, and then inside each logarithm I take the derivative with respect to mu k, and that means log derivative. So the function inside the log directly goes there. I change it from k to j in order not to confuse. So this becomes xj given theta j, right? And then the top part, you need to take the derivative of the top part for mu k. It's sum over k. I only take derivative with respect to one of them. So we can actually write this as a sum of L. Maybe it's better to write that way, actually. So we should write it as pi L, and then normal mu L. The kth one will be the relevant one. All others will zero out because there's no mu k in them. And then that one, the normal's derivative, pi will remain. So pi will remain as pi k, the kth one. And then the derivative of the Gaussian the first constant will stay as the constant. Exponent's derivative is itself. So this part actually remains as itself too. So this will be then mu k theta k. But then the derivative of the exponent will come as a term. So that's the chain rule. So following the chain rule, we got then minus 1/2 was there. So because this is quadratic, 2 will come here. This one will be then xk minus mu k. right? So this will cancel out. So this and this and this from chain rule, right? Chain rule. From chain rule of finding this. So, and that's actually more or less it. So from this, we've got what? So if we define this, is notice that this is the responsibility that I was talking about, and we can actually get rid of this by multiplying from on the right side with sigma k, and then that cancels that one out. So I end up with n sig the gamma. I should have said gamma, right? That's the gamma n. So we have gamma n here, and gamma n times xk minus mu k, xn minus mu k. So that should have been n actually, which gives me equals to 0, which gives me then mu k equals 1 over nk it gives me 1 over rk sum n gamma n xn here, with nk is defined as this again, sum of n gamma. Right, that's badly written n. Yep, that's not the Gaussian. Okay, so that's one of the formulas here, right? So, and the others are done in a similar way. The other one is the 925 is a bit cumbersome to derive. It's still you take the derivative, but it is much more involved. The last one is actually easier to derive. Maybe we can derive the last one with respect to pi k. Deriving this one is a bit easier. So we can just write it as ln p x given theta plus lambda times sum of k equals 1 to capital K pi k equals 1 minus 1, because the constraint is it is a probability vector, so they need to add up to 1 because it's a probability vector. So when you take the derivative of this with respect to lambda pi k, then it turns out and equal to 0. Then it turns out you end up with again similar to let me see. You end up with 0 equals n, and then that's the same as the gamma. No, it's not the gamma. So it's without the pi k. So it's n x n mu k, let's say theta k, and divided by sum over j pi j theta x n given theta j. Yep, plus lambda here, and from there actually with one more step we get here the lambda equals minus n, and because if we sum up with pi k and sum it up, this doesn't affect that, but if I sum it up with pi k, the top and the bottom become the same, so the denominator and denominator, they become 1, so you get n out of that. If I sum up sum over pi k gives you that, and then if you substitute back, you get the end result, and that's a ratio which gives you this one. So the long and the short story of it is there's a lot of algebra and so on involved here, but long and short of it is all we do is we are doing maximum likelihood for the thetas, which gives us, when we take the individual derivatives with respect to the missing parameters, those give us these equations, set of three equations, and this is just the additional definition to make the notation nice, right? So taking the derivative with respect to each of the parameters, mu and pi and sigma, the mixing vector, the mean, individual means of the Gaussian components, and then the covariance matrices of the Gaussian components. This is the multivariate case. That's why it's complicated. But you can imagine you can do it also single variate case. Then it would be just a Gaussian distribution on a line instead of a multidimensional Gaussian distributions. It gives you the result, and then that is used. These are used essentially in the expectation maximization to obtain the in an iterative process obtain their values. It turns out though that expectation maximization is much more general than just doing this, right? So we can use it for more general problems, and here's the overview of expectation maximization idea in general. So here we can actually extend this little bit by introducing missing variables z in addition to the observed ones in our data set. So then the complete data set becomes xz, right? So there are these x1s, but then there are these missing variables, latent variables that we don't know about. We only observe the x's. So if we want to do the same trick though, now we need to maximize the likelihood of pxz given theta, and then using maximum likelihood of this to find the theta, right? And then we know how to do this if we had this. But the problem is we don't have access to this xz theta. By the definition, z are the components that are not observable. That I only observed x. I'm only given the data set x. The z's are the missing or latent variables. So we can only estimate what z could be based on x. So it's a bit of a circular argument. I'm given x. I know there are some things that I'm missing, the z, and if I had those, I will use the same thing that I discussed in the special case. So I will do a maximum likelihood on pxz theta and then find the thetas. That would be, that would make me happy. But because I don't have the z's, so the best I can do is actually estimating the z's based on the x's and the thetas. So kind of can only know this pz given x and theta. So that leads to this two-step process. So what I do is I estimate this pz given x theta, and then using this estimate to maximize not the pxz given theta, but I maximize the px given theta, but the log likelihood of px given theta, but I take the expectation of this with respect to z to do my best in terms of z. So in the Gaussian case, we estimate the responsibilities, and then find the theta corresponding, maximum. Then we find the theta doing a maximum likelihood through using that log likelihood, where I use these responsibilities inside the functions, right? So that's a special case of it. That creates the two-step process. Here it's a bit nicer to understand the whole story. I wrote this as a verbal way. Here's the algorithmic way. You have the joint distribution, which we cannot obtain. We have only x at hand, and then we have the model px given theta with respect to theta, and I want to find this theta. So I choose initial thetas, like all the things that I have. Then I find, given the x and then my initial estimates, I find the p, the probability of z given these, and that's the probability that I'm going to use in the m step, where I want to maximize this q function, which is the expectation over z, which is the pz given this. So that's the probability that I'm going to put it, and then take the expectation of this joint likelihood log likelihood of this pxz. And then that together gives me something that is computable. And then I iterate over and over again. So this is a general form, and this is the specific form, right? In this case, the gammas are the responsibility, z's, latent variables. I don't know the gammas. And then I use the gammas, you see, they pop up everywhere. You know, in this equation, in this equation, in this equation, there are all gammas, which I estimated first in the expectation stage, the responsibilities, and then I plugged it in. So they become, in this case, the z's are the gammas. But there could be other methods, and then other methods may have different ways of handling this. I have these additional 2 slides, which I think may be giving. I don't know whether these slides make it better or confuses you. I guess I would like to ask your opinion on that. So it tells the same story in a slightly different way. Let me leave them here, not go over them, because it's talking about the same thing, expectation stage and the M stage. The difference here is instead of talking about the latent variables z's, here this talks about a complete data set y that I'm not observing, and then the observed data set x. And then talks about a mapping from y to x, because x is the only thing I'm observing. Y is the complete thing that I'm not observing. And then this relationship is used to derive the whole story with the same thinking here, the same expectations here, and then same derivative is taken here, right? Yeah, as I said, maybe we can discuss this, whether this alternative view is helpful or not. And I can skip it maybe next year, because I think these 2 slides already, general algorithm, tell a good story with latent variables. Some notes that should be mentioned. Why does expectation maximization work? Because, you know, that is just like we were talking about why does k-means work, there is a way of showing that E and M steps, they alternately compute a lower bound on this log likelihood that we want and increase it until the maximum. So each of them pushes this up. Just like k-means was pushing the cost down at each iteration, these are pushing the maximum likelihood estimation up. So, and because they do it consistently, you end up with the solution. So that also converges. But that analysis is pretty involved. A lot of heavy, math there. It's in Bishop section 9.4, or you can see Barber 11.2. Then if you are interested, go and have a look. But end of the story is each of the steps at each iteration, E and M steps, they push a lower bound on this up, and therefore, because the lower bound goes up, the thing has to go up as well. And as you iterate, it finds the solution when it can. But then it's not always perfect. So there may be singularities when one component has a mean that is exactly matching a data point. If by chance the mean of the component has the same as the value of a data point, then the algorithm gets into trouble. And then the other thing is, you may end up again with a lot of local solutions, because a k-component mixture can have k prime, tons of different solutions to the same problem. So there are a lot of different ways of assigning parameters to these k components. So that's also an identifiability solution. So you may end up with a model. Two of you solve it in different ways. You end up with 2 different models. They are equivalently good, but they look very different. So in that sense, that's a bit of a problem, too many solutions problem. And we did it with maximum likelihood, right? You can also use it for map maximum a posteriori if you have a prior on your parameters. Remember, if you have a prior distribution on your thetas, you can actually use it to map. If you don't have priors, I don't know what these thetas are, you do maximum likelihood. We did the maximum likelihood. We put the log likelihood, right, for this. But you can also do the map version. And then the last word I want to say before closing is k-means versus expectation maximization. Actually, one can show that if you take the limit of EM, you end up with k-means. So that's a nice result. So because k-means does a hard assignment, right? There is this assignment function, 1, 0s, depending on which cluster you belong to. And then it turns out these responsibilities are a softer version of this. And then when you find the mean, you see in the M step, the means of the parameters, they are with the responsibilities. If you put instead of responsibilities R's, then it's the same thing. You see, they look the same. So actually, I have put a question. I put it as a question. The argument is very simple. When you look at the solution, the argument is very simple. So it goes to the idea of the softmax function. This is called the softmax function, e to the beta z and sum of e to the beta z case. So as beta goes to infinity, this softmax function is actually a 1, 0 function that finds the maximum. And notice the responsibilities. It has all these e to the beta structures here, right? And then have an epsilon in the denominator. As epsilon goes to 0, that is same as beta going to infinity. And the responsibility is like a softmax function. As epsilon goes to 0, variance goes to 0, then it will go to a 1, 0 proper maximization, finding which point belongs to which cluster. Instead of the soft probabilities, they converge to hard assignments. And once they are converged to hard assignments, once you replace the gammas with R's, then you also end up with finding the prototypes. So you have both steps. Making hard assignments and finding the prototypes is k-means. Doing soft assignments and finding the other stuff is the expectation maximization for Gaussian mixture analysis. So the EM re-estimation then for that specific problem reduces to the k-means if we have this in the limit of when we take the responsibilities and then take the limit with epsilon goes to 0. And that's, as I said, is equivalent to softmax function becoming a hard assignment function. So that is an interesting result. It's also kind of somewhat intuitive if you think about it. What we are doing with pictorially, what we are doing with again, these pictures are pretty nice to keep it in mind. You know, like these. So what we are doing is, you know, when we do the mixture analysis on the probabilities, so we are taking the data points and representing the data points with these, you know, Gaussian blobs, so to say. And if you take the limit, it is a bit like putting those data points into clusters, individual k clusters corresponding to these k data points. So in a sense, taking the limit of that process gives you you end up with a k-mean hard clustering. Here it is softer, so it's a probability distribution. So maybe that's a kind of an intuitive connection, visual connection between the two. Same with the one-dimensional case here. So all of the stuff that looks very complicated that I covered, especially for question 4. Maybe I should have put it in the one-dimensional case. Then all of those matrices and mu's become scalars, matrices become the variances, sigma square case. The derivation would be much simpler, and they're much more achievable by doing by hand. But don't you know, get scared by this taking the derivative of this with respect to these individuals. Derivative of this with respect to individual components, right? Unknowns, these are the 3 unknowns, and then you take the derivative of log likelihood with respect to those to find the best solution, and then that's the basis for the iterative process. You can use also symbolic tools, right? As an engineer, right? Forget about the subject. You know, if someone asks you to do this in a job, you know, I would go to Mathematica and then make the Mathematica take the derivations for me. So that's another option. Like, you know how to use MATLAB, or you go to the MATLAB symbolic toolbox. You know, it's just you give it to it, define the symbols as vectors, but then it's still feasible. And then if the vectors are predetermined, I suspect, I haven't tried it, but I suspect Mathematica will give you the very nice derivatives. So then you have the symbolic solution as well, in addition to the numeric solution. So it's not a big deal, to be honest.